we will discuss triclinic. We have discussed triclinic, monoclinic, orthotropic. In a similar fashion, we will discuss cubic and continuum. Isotropic. 5 continua. After these 5, we have 3 more. They will be discussed in a different manner. Now, in this lecture, we will discuss only elasticity matrix for cubic material and isotropic material. Now, for cubic material, you have 3A2 axis, x1 axis, x2 axis and x3 axis, and angle of rotation will be 2 pi by 2, that is pi. And you have 4A3 axis as symmetric axis, in addition to center of symmetry. In addition to center of symmetry means that center of symmetry exists for all types of material: triclinic, monoclinic, isotropic, cubic, orthotropic. But we know that as center of symmetry does not play any role in decreasing the number of independent components, so we will not discuss this center of symmetry further. For cubic, we have 3A2 and 4A3. These are x1, x2 and x3 axis. Angle of rotation is 2 pi by 2 n. And we will see that what are 4A3. Now first, a center of symmetry, we know that this symmetry plays no role. 3A2 axis mean angle of rotation is this, and you will take x1, x2 and x3 axis parallel to A2 axis. A2 means 2 pi by 2, and repeat the whole procedure as we have done for monoclinic material and orthotropic material. So when you will apply 3A2 axis, then you will reach at the result of orthotropic, which is this equation number 1. Here we have 9 independent. Up to here we have applied 3A2 axis, x1, x2 and x3. But we have more symmetric axis. There are 4A3. Now what does this 4A3 mean? A3 means that we have angle of rotation 2 pi by 3. What is 2 pi by 3? 2 pi by 3 is 120. That we have angle of rotation 120. And now we will see that these 4 axes, as we have seen that for A2 we have x1 axis, x2 axis and x3 axis simply. And what are these 4 axes in which we have take rotation 2 pi by 3? These 4 axes are basically the diagonals of cube. You can see that if you have cube like your room, that you can see that joining the opposite corner of your rooms, you will have 4 diagonals joining the opposite corner. One corner from the roof and one corner from your floor. Then you will have 4 diagonals. About these diagonals we have to take the rotation. And rotation of what? Rotation of 2 pi by 3 with an angle 2 pi by 3. Let us consider we have this type of cube, and we have there, this is R100, this is RZ001 and this is Y010, and this corner will be joining these and these. This will be 1100, and this is the center 000, and this will be 101, 10, and this one 101. This will be 10, and this will be from these two we have 0, 0, 1, and 1 1. Yeah, this is this is in the plane YZ, and this is in the plane XZ, and this is in the plane XY, and this is at the origin, and this is in the space 1 1 1 1 1 1. Now to understand, let us consider that we are writing 111 as 1, 101 as 2, 100 as 3, 4, 110, 5 as 001, 6 as 011, 7 as 010, 8 as 000. Now further, to check that how can we apply this, let us press the cube from any opposite corner. That if you press that cube, then you will have a hexagonal on your paper, an hexagonal on your paper, in which this is your 1 and 8. 1 is 111 and 8 is 00. Origin and space corner, they will be joined each other here, 1 and 8. And now this is your 2, this is your 5, this is your 6, and these 2, 5, 6 are telling that these are the corners. That this is 2, 2 means 100. This is 5, 5 means 001, like 6, 7, 4 and 3. Now here we have your 4 diagonals. From 1 and 8, one diagonal is this, 1 and 8, and 1 is this, 4, 5, 1 at this, 2, 7, 1 is this, 3, 6. Now for hexagonal, you know that this angle is 120. This angle is 120. Fourth diagonal will be from opposite corner 1 and 8. And first from 3 and 6, 3 and 6, 4 and 5, and last third is 2 and 7. Joining the 2 and 7 means that joining 2 and 7 corners. These are opposite corners. So when we rotate through an angle of 120, then you can see that by applying this rotation, this is 120, this corner will be at 7. When we complete this 120 rotation, 3 will move to 7, 3 to 7, and your 7 will go to 5. These lengths are same. Okay, these lengths are same. You can check 1 1 1, and 5 will go to 3. 5 will go to 3. And we know that what is 3? 3 is 100, that is x1. And what is 7? 7 is 010, that is y. And what is 5? 5 is 001, which is x3, again 3, and again we have 3. So x3 is 1, so x1. So it means that by applying this symmetry, x1 will go to x2, x2 will go to x3, and x3 will go to x1. So we have 1, we have 2, we have 3, and we have 1. That 1 will go to 2, 2 will go to 3, 3 will go to 1. So we will use this to know about the independent components. And we have 9 independent components so far. Given equation number 1, here we have written, there we will apply this on equation number 1. Let us take C12. C12 will go to, as 1 will go to 2, so C2, and 2 will go to 3, C2 3, and C2 3 will go to, as 2 is going to 3 and 3 is going to 1, C3, and C3 1 will go to, 3 is going to 1 and 1 is going to 2, so C12. So it means that C12 will equal to C23, C23 will equal to C13. They all are equal. No, the diagonal components. C11 go to C22, C22, C33, and C33 will go back to C11. So C11 will equal to C22 and C22 equals to C33. Now we have other three diagonal components which are C4 for C23, C23 basically C23, so we as we have no 4, so we will write this 4 into your 4 index notation. 4 at 4 we have 2, 3 and 2, 3. So this will give us 1, 2 will go to 3, 3 will go to 1, 2 will go to 3, 3 will go to 1. So 3, 1, 3, 1. Again we have 3 will go to 1, 1 will go to 2 and 1, 2. Again here we can apply 1 will go to 2, 2 will go to 3, and we have again this. So this will give you C4, 4, this is C5, 5, and this is your C6, 6. So at the end we have this type of result, that C11, 3 diagonal components, first 3 diagonal components are equal, second are also equal, and the non-diagonal components C11, C12, C1 they are also equal, same. So you can see that we have left only 3 independent components, which are C11, C12 and C4 from. So isotropic continuum. In isotropic continuum, every orthogonal transformation is symmetry for this continuum. As we are saying, there is isotropic continuum. So the elasticity matrixCijkl, this must be isotropic for this continuum. So we will see that with the help of some other isotropic tensors, that how can we proceed to calculate the independent components of C for this continuum. As we are saying this is isotropic, so we can also look some other isotropic continuum, isotropic tensor which have order 4. You know that there is the Kronecker delta tensor of order 2 which is isotropic. Now what the isotropic means, I have explained, I think, from in the start, that what is isotropic. Isotropic is basically, isotropic tensor is basically which is tensor which has same number of, which has same components in every coordinate system. That if you have transformed the coordinate system, then this components of this tensor will not change, and that tensor is called isotropic tensor. Like delta has 1 0 0 0 1 0 0 0 1. Then in any coordinate system, this with transformation in Cartesian coordinate system, any Cartesian coordinate system with the help of transformation, with any transformation, any rotation, then this components will not change, and all the components will remain same, 1 0 0 1 0 0 1 0 0. That is, if you have delta 1 1 equals to 1, delta dash 1 1 will also be equal to 1. Delta 1 2 is 0 and delta dash 1 2 will be 0. Whatever the rotation is, whatever the transformation matrix is, that how you are transforming one system to another system, this does not change the components of this delta. So with the help of this second order tensor, we have 3 independent fourth order isotropic tensors. These are 3 independent fourth order tensors, isotropic tensor. Delta ij, delta kl, delta ik, delta jl, delta il, delta jk. If you want to make another combination of these indices, by changing these indices, you will have the result from these 3 again. So there are only 3 independent choices. So asCijkl is isotropic, so we can write thisCijkl in the linear combination of above 3 isotropic tensors: lambda delta ij delta kl plus mu1 delta ik delta jl plus mu 2 delta il delta jk. By changing I and j, we have this. You can change also k and l, but you cannot apply the pairwise symmetry, and you cannot change ij with kl, because on the right hand side we cannot do this. Cji kl will be equal to cji. Here will be mu1 delta jk delta il plus mu2 delta jl delta ik. These are same left hand side because of symmetry of C in first pair. It means that right hand side will also be equal. This will be cancelled with this. These are same, and mu this and this will be taken as common, and we have mu1 minus mu2 into this plus mu2 minus mu1 equal to this, and we have said that these are independent. So due to independency, this is equal to 0, this is equal to 0, we have mu1 is equal to mu2, say mu, they are equal. So we have this. When we have this, then you can see that in your cubic continuum you have diagonal components. First 3 diagonal components are same, second 3 diagonal components are same, and other 3 of diagonals are same. So you have to check only 3 components. C111 first, it will be lambda delta 11 delta 11 plus mu delta 11 delta 11 plus delta 11 delta 11. So lambda into 1 plus mu into 1 plus 1 lambda plus 2 mu. So first 3 diagonal components will be lambda plus 2 mu, lambda plus 2 mu, and lambda plus 2 mu. Last 3 diagonal components, they are same, C44. So C44 can be written as C2323. So it would be lambda delta 23 delta 23 23 23 plus mu delta 2332, j is 3 and k is 2, delta, this is delta 23 plus delta 33 j3 and l3 delta here j3 l3 j3 l3, and I and k, they are ik and k2, so they will be delta 22. So we have, this is 0, this is 0, and we have mu, this is 1. Because of 1 we have C4 is equal to mu. So other 3 diagonal components would be mu, mu, and mu. So we have left with the off diagonal components. They are C12, they are C1122 delta 11 delta 22 plus mu delta 12 delta 12 plus delta 12 delta 12. This would be 0, this would also be 0, and we have only C12 equals to lambda. So we have this type of elasticity matrix or isotropic continuum. Lambda plus 2 mu, lambda plus 2 mu, lambda plus mu, mu, and mu, lambda, lambda, and lambda. So you can see that this here is only 2 independent elasticity constants, lambda and mu. If you have lambda and mu, you have whole this matrix C with the help of these 2 numbers, the lambda and mu. These are constants, and these constants are basically called Lamb's constant. Their value in terms of C's are this: lambda is equal to this and C mu is equal to this. Their dimensions would be same as constant C, and you know that the dimension of constant C is Newton per meter square. This is coming from T is equal to Tij equals to Cij KL SKL, and we know that S strain is independent, dimensionless. And what is dimension of stress? Dimension of stress is Newton per meter square left hand side. So also dimension of C would also be, component C would be Newton per meter square. Now we will write stress strain equation for isotropic antenna. This is the stress strain equation. By putting the values of this Cij for isotropic, we have this as SKL here, this SKL. Now what you will have to simply do, you have to multiply this into the brackets. This would be delta lambda delta ij SKL and delta KL plus mu delta ik delta GL SKL plus delta JK delta IL plus into SKL. Now by using your previous knowledge about the indices, summation of indices product of delta with any tensor, and after 3 to 4 steps you will have this type of equation. This is stress strain equation for isotropic container. This is lambda skk delta ij. What is skk? This is basically strain s11 plus s22 plus s33, and delta ij, you know that what are the values of delta ij. This is 2 mu sij. Again, this is strain sij.